Sounds good. Thanks everybody for sticking around. So Inga is here, and she said she'd be available to answer questions. Sean is not here. I should say that Sean is a former PhD student of mine. So the general set of issues that we're trying to look at is communication in context and settings in which somebody can shape that communication but has limited ability to do so. Oops, let me go to the next slide. Yeah, here we go. So I will iterate through the problem that we're going to look at like 3 or 4 times. Eventually there's a version of it that will be a model and has notation, but I'll just quickly summarize what a setup is here before I jump into that. So the puzzle that we're looking at in this paper is one where you have a principal who expects to receive private information, but has to rely on an agent to act on that information. The principal would like to shape the way in which the agent handles the information, but it has limited power to commit to state contingent instructions. On the other hand, the principal can always talk. So there's always a possibility for cheap talk communication. And then the question that we're trying to answer is, what is the interaction between the ability to commit and to issue instructions, or the limited ability to commit and to issue instructions, and the ability to communicate. Okay. So here's a bit more detail that gets closer to the model. So we have a principal who, prior to receiving private information, has the ability to write a contract. The contract, however, can only be cannot be fully detailed complete, and we just justify that with writing costs. The principal may choose the contract to not be obligationally complete, and by not obligational completeness, we mean that he can choose to not cover all different contingencies. So after writing the contract, the principal receives the information, and then there's some information that is governed by the contract, and then there will be some information that the principal may choose not to have be governed by the contract, and then transmits the information, and then the agent acts either in response to an instruction from the contract, which is entirely governed by that contract at that point, and there's nothing more to analyze, or through cheap talk communication in case we have reached a contingency that is not explicitly covered by the contract. And then state contingent actions, which will by assumption be coarse, will be strictly enforced. So to repeat the earlier question here, what we're going to ask is what information will be governed by the contract, and what information will be governed by ad hoc cheap talk communication. And so how do the two things, contract and cheap talk, interact? So again, a bit more detail here. The timing is as follows. There's a stage 1 in which the principal writes a contract. And what the contract does is it codifies language that makes conditions, sets of states, and actions, instructions, verifiable to third parties. So in our contracts, there are no payments. In particular, there are no contingent payments. We have a little example that looks at individual rationality constraints and non-contingent payments, but in the talk, I will almost completely ignore that. So then at stage 2, the principal observes a state. The principal will send instructions according to the contract in case a state is covered by the contract, or send a cheap talk message in case there is a gap in the contract. Ad hoc communication, or cheap talk, is viewed as informal, private, and non-verifiable. And then the agent takes an action by following either an instruction if an instruction is issued, or by responding to a message if the contract doesn't cover the state and the principal engages in cheap talk. And then at the end, contracted states and actions become verifiable. So everything that was governed by the contract will be strictly enforced. So in terms of literature, obviously we live in this world of communication of Crawford and Sobel. Contract writing costs have been appealed to by Dye. Battigalli and Maggie have a more detailed model that thinks of writing costs in terms of details of the language. Most closely related to what we do is probably a paper by Chevelle and a related paper by Heller and Spiegler, both of which are concerned with contract interpretation. So in their world, you're writing a contract. The contract has clauses that cover some states but not other states. And then in Chevelle's case, there are interpretation issues both when the contract doesn't cover a state, but also potentially in the case where there are states that are governed by the contract. And then Heller and Spiegler look at a version of that that allows for contradictions in the writing of the contract. Neither of these two setups allow for communication. So in some sense, you can think of what we do as superimposing communication on their setup. So what happens then is that once you have the contract in place, the way we write up our model, you effectively eliminate the states that are governed by the contract from consideration for the communication. And if you look at the communication literature, that happens endogenously in, like, say, Almond Hart setting or Krishna and Morgan, where prior communication reveals something about the state and excludes some of the types, and then basically reduces the continuation game to one where you have the prior being concentrated on just a subset of states. Okay, so that gets me to the formal setup here. So since we are primarily concerned with communication here, it will be convenient to change the names of our actors here. So the principal will become a sender, and the agent will become a receiver. So I will, from now on, just talk about senders and receivers instead of principals and agents. There's a state that is drawn from some distribution on the unit interval. The receiver takes an action in R. So this is just, the Crawford-Sobel setup, if you're familiar with it. The payouts depend only on the action Y that the receiver takes and the state of the world. And there's a difference in preferences between sender and receiver payoffs. And it will be convenient to have that be parameterized by a parameter B that we'll refer to as a bias. And we look at the positive bias case. So for any given state, the sender prefers a higher action than the receiver. The sender's ideal point is always above the receiver's ideal point. So here's the timing again and a little bit of related notation. So at the beginning of time, before having any information, the sender writes a contract, script C. So we're referring to the contract timing game here as G, and then later on there's going to be a communication subgame gamma. So initially a contract script C is written. And that contract by necessity, by assumption, is not fully detailed complete, meaning it doesn't specify what to do for each single state of the world. Instead of that, it bunches states of the world and then assigns instructions, prescriptions for those sets. Now, the sender, when writing a contract, may choose not to cover all of the states. And if that happens, then that gives rise to a gap in the contract. And if there's a gap in the contract, that creates an opportunity to communicate. So intuitively, if you can write only coarse contracts, that limits your ability to tie the action to the state. If you leave gaps, and there's the potential for communication, that may make it possible to tie the actions of the receiver more closely to the state, especially if the incentives are closely aligned between sender and receiver. So after the contract is written, the sender observes the state. In the case that the contract governs the state, nothing more happens. It just, in the model, there's an action that is induced. If, on the other hand, the contract doesn't govern the state, then we're in the gap, and in the gap, we'll have communication. So in the case of a gap, we reach a communication subgame. We denote this communication subgame here by gamma C. Once we're in gamma C, the sender sends a message. The receiver takes an action. And what we're interested in is to characterize the sender optimal subgame perfect equilibria of this game. So the sender optimally chooses a contract, and then that contract in some cases leads to a communication subgame, and then in that communication subgame, the sender optimal equilibrium is played. So we're doing equilibrium selection here in the communication subgame.
Andreas, just a clarification. So are there restrictions on what the so when you say that the contract must be simple, is that an exogenous restriction, and sort of what is the restriction exactly?
That is an exogenous restriction, and I believe that is on the next slide. Oh no, it's actually, well, yes and no, right? So I'll spell out the model in a moment here. So the way the contract is simple is that there are conditions in the contract, and for those conditions you have instructions. We allow for only finitely many conditions, and a condition has to be an interval.
Okay.
Right. So if you go to the next slide here, so this would give you an example of a contract. This is a contract that has 3 conditions: C1, C2, and C3. Each one of those conditions is an interval. And the contract specifies here for the interval C1 that action X1 is taken. For interval C2, it specifies that action X2 is taken. And finally, for C3, X3 is taken. So the X's are instructions. The C's are conditions. The conditions we assume exogenously to be intervals. Okay, so once this contract is in place, if we reach a state that is outside of one of these conditions here, then the sender gets to send a message. At that point, there's no instruction that pins down what to do. It's left to the receiver to take an action, but the receiver can be influenced by cheat talk. Okay. So an equilibrium might look as follows here. So of course, given the conditions, nothing happens. So we really have a cheat talk game that arises from having the prior being now restricted to everything that is outside any of these conditions. So the complement of the union of the conditions gives rise to a cheat talk game with a prior restricted to that complement, right? And so here's sort of an example of what an equilibrium might look like. It could be that from 0 to theta 1, one message is sent, and that induces the action Y1. And then there is another interval from theta 1 to up to the condition here in which action Y2 is taken, right? And then there's another communication interval that goes up to theta 3 here in which yet another cheat talk action is taken. And so the equilibrium has you can easily show has the conventional CS partitional structure. So there will be a set of critical types here, theta 1, theta 2, theta 3, that induce these three different cheap talk actions, Y1, Y2, and Y3 in this game, right? Okay, so here, so this should answer Naveen's question in full detail here. So a contract, remember contracts don't involve payments here. They're basically just dictates from the sender. So what a contract does, it provides clauses. So in this contract here, there are K clauses. And a clause has two components. It specifies a condition and it specifies an instruction. And so that's very similar to what happens in Chevelle and Heller and Spigler. Conditions we assume to be intervals in the state space. And the rationale is, we're living in a world where contracts have to be simple. If you want to have instructions associated with sets, we want those sets to be simple. What are simple sets? Intervals are simple sets. And then for each of those conditions, the contract specifies an instruction. And we denote instructions by X's. The other way we have simplicity is in that there can only be finitely many clauses, and we denote the maximal number of clauses by K hat. Okay. In the event that a state is realized that belongs to a condition, then the corresponding instruction is implemented. So in the little graph here at the bottom, we have two conditions. In condition 1, X1 is implemented. In condition 2, X2 is implemented. And this doesn't say anything about what happens with cheap talk. Now, the sender may choose not to cover all states in the contract. And if that happens, then we arrive in a gap. So a gap is just the unit interval minus everything that is covered by a condition. And we get a cheap talk game by restricting the prior to that gap. And in that cheap talk game, the sender sends a message from some sufficiently large message space. And the receiver takes an action in response to the message. And as usual, we don't have to worry about mixing for the receiver. We also allow for the possibility of not writing any contract at all, in which case we're just back to the usual CS game. In the cheap talk game, there's no commitment. And I said already that equilibria, as usual, are partitional. And we refer to the partition elements as steps here. So here again would be a one-dimensional representation of an equilibrium like the one that I showed you earlier. So here there are two conditions indicated in blue. The instructions are left out here because we're only interested in the cheap talk. We have three critical types here, theta 1, theta 2, theta 3. So there's an interval here from 0 to theta 1. So that all of those types in that interval would like to, they prefer Y1 as the available action, and then above that they prefer Y2. Notice, however, that, and that will be important later, the critical type lives inside of the condition here. So the incentive constraints are actually really not binding at that point, right? Really what's important for the equilibrium is the types up to the lower bound of this condition here prefer the lower action to the higher action, etc.
Andreas, maybe I can bring a question to you from the Q&A. So the question is sort of, in the model, the instructions here have to be singletons, so they specify actions for particular states. And Heskey asks whether you couldn't consider, all you do is you rule out certain actions rather than prescribing a particular action or things like that, and is that part of simplicity?
So there are many different ways in which you could sort of modify things. So for example, you could just so one of the things that we're looking at right now, for example, is that you only specify instructions and that the sender then can choose from. The other possibility is that the sender commits to just reveal sets in states lying in a certain set and then not specifying an instruction, which is sort of in the spirit of the question. And then within that framework, I think there are sort of other ways of looking at it. So we haven't looked at that. Basically, what we are doing here is in this version of the model, we are very sharply separating the cheap dog game from what the contract specifies. If you don't do that, if, for example, you only specify instructions and not the conditions that go with them, that really makes the incentive problems a lot harder. So that's something that we're looking at right now. But it's true. I mean, there are many different ways in which you could look at this. We are basically just borrowing the world of Chevelle and Heller and Spiegler, in which you have instructions and conditions. All right. Thank you. So here's the simplest possible example that you could imagine here. We're looking now at the case where we're looking at quadratic loss functions. So this is the uniform quadratic world of Crawford and Sobel. So it's a uniform type distribution and these two quadratic loss functions here. We are looking at the case of a single clause. So you can specify a single condition and a single instruction to go with it. And we're looking at a bias that is equal to 1/3. Yeah, for those of you who remember, so in the Crawford-Sobel world, you only get influential communication if the bias is less than a quarter here, right? So we're picking a bias so that with only communication, nothing interesting happens, right? And we want to find out what the optimal contract is here and the optimal and an optimal equilibrium associated with that contract in that case. And in that simple world, there are really only 4 possible cases for contracts and associated equilibria. So you have the option of not writing a contract at all. That takes you back to communication. And since the bias is equal to 1/3, greater than a quarter, only babbling is a possibility here. So the receiver will take the midpoint of the unit interval as the optimal action. The next possibility is that the sender writes a contract that covers everything. So that's indicated by the blue here, covering the entire unit interval. If the sender writes such a contract, then associated with that contract would the natural optimal instruction is to pick an instruction that is equal to the midpoint plus the bias 1/3, right? So now instead of getting the receiver optimal action, you get the sender optimal action. So there's an obvious benefit to the sender. So the obligationally complete contract here already improves outcomes for the sender. But then you can ask whether there's a benefit potentially for combining that with communication, right? And remember that in Crawford and Sobel, there's no communication possible with a bias of 1/3. So with communication, there are 2 possibilities here. It's easy to see that it's impossible to induce 3 different actions through communication. So that leaves the possibility of inducing 1 action through communication or inducing 2 actions through communication. That's on the next slide here. So we call that 1-step and 2-step, referring to the number of communication steps. So on the top here, we have the optimal contract for 1-step communication. So here you have an interval that goes from 0 to something around 3/4 or something. So that would be the condition in the contract, and then there's an associated X, which is the midpoint of that interval plus 1/3 plus the bias, right? And then if the state doesn't fall into that interval, then the sender sends a message, and so that informs the receiver that he is free to choose whatever action he wants, and he will pick the midpoint as an action. It turns out, so what I present here is actually the optimal one-step communication contract, and this optimal one-step communication contract you can numerically show improves on no communication. Right? So you get the benefit of making the state more sensitive. Sorry, making the action more sensitive to the state by allowing for communication here. But there's also the possibility of inducing two different actions here. And this is what we mean by allowing for two-step communication here. So if you allow for two-step communication, then the optimal contract has the following form here. There is now an interval that is exactly in the middle here of the unit interval. The associated instruction is again the midpoint plus of that interval plus a third. And then at the two extremes of that interval, you have communication inducing actions y1 and y2, both of which are the midpoint of these two intervals. And you can numerically show that these four possibilities here are strictly ordered in terms of the sender's payoff. The sender clearly prefers to have a contract with no communication to no contract, but also prefers to have either one-step communication or two-step communication, with two-step communication being best in this case. So the fourth possibility actually does show you what the optimal contract is. So to look ahead a little bit here, one of the things that the contract does here is to, in addition, benefiting the sender directly by allowing the sender to specify her conditionally preferred action, it allows the sender to relax incentive constraints and enable communication where there would be no communication otherwise. Right. So remember Crawford-Sobel, no communication with the bias of 1/3. Here you get communication, and you actually do want to take advantage of it. It is optimal to induce maximal communication here if you want. Okay. Now you can change the parameters here a little bit. So let's play with this a little bit. The first thing we'll do here is look at the case where now we allow for two clauses. So k hat is equal to 2, and you're keeping the bias constant. Well, in that case, it turns out you don't want to induce any communication. You just want to have these two clauses split the unit interval equally, and then you just induce your sender preferred actions for each one of those two conditions. And in the last example here, we just go in reverse. We now keep the number of clauses constant at 2, but we're reducing the bias down to 1/5. Now, and there it turns out you actually want to. So if you just as a reminder again, so without a contract, you could maximally induce 2 actions, but here you can induce 3 actions, and you actually want to do that. So this gives you a graphical representation of what the optimal contract looks like. Right. So there's some preliminary takeaways here from these examples. Clearly having more clauses allows you to improve payoffs. That they can't harm you. More clauses can drive out communication. So that was this example here. Communication can replace contracting for smaller bias. That's sort of switching from this example to the lower example with the lower bias. And if you compare this to CS, you see that contracts allow you to relax incentive constraints for communication, which sometimes allows you to induce more communication. And sometimes that's also optimal. Okay. So we have results of two kinds. So it turns out that working this out in detail is actually a bit of a pain. So we have a couple of results that apply to a general setting with general distribution functions and general pair functions that are quadratic, sorry, not quadratic, that are concave and have a positive cross-partial condition. So if you only assume that, then you get the following. You do want to use as many clauses as possible, always. So you always want to max out at k hat. And so why is that the case? Well, suppose you didn't use any clauses, then you would have a partitional equilibrium in the CS game. You could just take one element of the partition, replace it by a condition, and then rather than having the receiver take the receiver optimal action, have the sender impose the sender optimal action there. So that gives you a payoff improvement, and you don't mess around with the incentives. So that means you want to have at least one clause at a minimum. Once you have one clause, you can always benefit from slicing that clause into smaller clauses and improve payouts. Right? So that's the proof right there. One comment here. So Inga and I actually are working right now on a related story where you only specify instructions, but not the conditions under which the instructions are chosen. And there you can actually show that if you have a sufficient degree of conflict, you don't want to max out on the number of clauses. So maybe this observation is not as obvious as you might have thought. So the second result that applies to the general setting, also very intuitive, is that if you increase the maximal number of clauses and let it grow to infinity, that will drive out communication. So for any sequence of gaps that arise in sender optimal equilibria of this content writing game, as you increase the number of clauses, the probability that you end up in the gap goes to 0. So more clauses means, regardless of what the bias is, means less communication. And then there is the converse that holds under a technical condition here that says that for any sequence of gaps in sender optimal equilibria where the bias goes to 0, the probability that you get a gap goes to 1. So basically that means that as the bias gets small, as incentives get more closely aligned, despite the ability to contract, you want to primarily rely on communication. And then the rest of the paper concerns the uniform quadratic world. So just to go back here. So we now go to the world where you have a uniform distribution as your prior, and the payoff functions are as described here, where you have quadratic loss functions with a constant bias. So so in this uniform quadratic world, and not looking at optimal contracts right now, it's not hard to see that by choosing your contracts judiciously, you can enhance the possibilities for communication. So basically what this is saying is that if you fix any b, then you can find a bound on the number of available clauses and an associated contract such that in the associated communication subgame, the number of induced actions is bounded by 1 plus 1 over 2b. So that gets interesting once you relate it to the Crawford-Sobel bound, which is on the left here. So if you look at the case of b less than a half, then the Crawford-Sobel bound is strictly less than the bound that we have here. And if you look at a bias of 1/10, and you make the k hat arbitrarily large, then under CS you get 2 communication actions induced. And in this world, if you wanted to, you could induce 5 different communication actions. We can also make the result that with many clauses, the probability of communication going to 0 more precise here. So if k hat, the maximum number of clauses, is greater than 1 over 2b, then any optimal contract will be obligationally complete. There's no communication at all. So with a sufficiently large number of clauses, you don't want to communicate. You want to have everything be taken care of through the contract. Okay, so let me slow down a little bit here. In a way, this is the central result of the paper, and here I will actually give you also a slightly more detailed argument for how we arrive at that. So the main point of this result here is that optimal contracts will use contracting not just to help the sender impose sender optimal actions, but also to relax incentive constraints for communication. Right? So one term I would like to introduce is that of a condition cluster. So we don't know in general whether conditions will be separated, whether we have the intervals be disjoint, or whether in some cases they cluster. Right? Of course, if you have an obligationally complete contract that covers everything, then clearly you have clustering. And so the result that I will give you is in terms of condition clusters and what condition clusters do vis-a-vis these critical types in the communication game. So in words, what the proposition says here is that in a sender optimal equilibrium under an optimal contract, every condition cluster will contain a critical type. Putting it differently, condition clusters never belong to the interior of a communication interval. So if you think of the intervals in Crawford and Sobel, and you now combine that with contracting, you would never put a condition or a condition cluster strictly inside one of those intervals or the analog here. Moreover, if you look at influential communication, so where communication is actually interesting and induces multiple actions, in any optimal equilibrium under an optimal contract, there will be a condition cluster that not only contains a critical type, but also a critical type that is not 0 or 1. Right? So on the top here, we include 0 and 1 among what we call critical types. Here we show that if there's influential communication, interesting communication, then there will always be a condition cluster that covers an interior critical type. So let me just read through the proposition here. It's probably not strictly necessary, but why not? So suppose that the contract script C here that consists of conditions CK and instructions XK, and we know that we're using all the conditions, all the maximum number of conditions up to K hat. Suppose that is optimal in this contract writing game, and suppose that the equilibrium EC that is sender optimal in this communication subgame, then for every condition cluster in the sender optimal equilibrium, there is a critical type C theta that lives inside of that condition cluster. If in addition this equilibrium EC, it induces at least 2 communication actions, so it's influential, then you can find a condition cluster that contains an interior critical type. Okay. So this is what took us the most work to get. And what I will do is I'll give you a simple little intuition with only one condition.
Andreas, if I can just interrupt for a second. So we
Yeah.
have about 3 minutes left, just so that you know how to allocate your time.
How many?
3 minutes.
3 minutes. Oh, so I thought I had until, oh, I get it. Sorry. I lost track of time. Yeah, that works out actually pretty well. So we're looking at a scenario here where you have initially a condition that lives inside of a communication interval, right? And then we have some equilibrium associated with that, indicated by these critical types here. And what I want to do is I want to improve on that hypothetical equilibrium by moving this condition around, right? So the first thing I'll do is I move the condition from the inside of this communication interval all the way to θ1 here, right? And notice, ignoring incentives for the moment, if the receiver now responds with a midpoint action to this interval here, because we're reducing variance in this interval up here, that improves payoffs, right? So there's the first red arrow gives you payoff improvement. Of course, we have an incentive problem here at θ2 now, because θ2 now prefers the lower action. We can fix that incentive problem by re-equilibrating above the condition here, moving y1 up, y2 up, moving θ2 up, and moving y3 up. And that equalizes these communication intervals. So that gives you an additional payoff improvement, plus it fixes the incentive problem here. Now, the next problem is that we may have an incentive problem here, because that type, now given that y2 moves up and y1 stays in the same place, might now prefer y1. The way we fix that, we just move the entire condition up here, right? And at the same time, we're maintaining incentives up here by moving the θ2 up. The only way you can have an incentive problem here is if this interval here is shorter than that one. So that means that we're overall equalizing the lengths of these communication intervals, and so that gives you an additional payoff improvement, right? So that's a fundamental idea. Now, in the general case, where you have many conditions, you have to do this from the top, and you have to do it many times, and you have to keep track of being able to maintain incentive compatibility throughout. But that can be done. So I have the feeling that I'm getting to the end here. And so maybe I should just put up my finishing slide here, the concluding remarks. So we built a model of interaction between contracts and communication. There's a trade-off between ex-ante commitment and exposed discretion. At the extremes, if you have small disagreement, communication dominates. If on the other hand, you have many clauses, then contracting dominates. The principal insight here is that what the contracts allow you to do is not just to shift control to the principal, but also to allow relaxation of incentive constraints. And the relaxation of incentive constraints makes it possible potentially to induce more actions, and also to even out the communication in the sense of equalizing the lengths of the communication intervals in this uniform quadratic setting. And that gets me to my last slide. Thank you.